Hi, Mick McQuaid here, welcoming you back to iste780 Data-Driven Knowledge Discovery. This is the third and I think last video for day 2, and I want to mainly talk about the homework. Before I do that, though, one thing that I missed before is the issue of regression and classification problems. So it is the case that all of our variables could be construed as quantitative or qualitative. And by quantitative, we mean that they naturally take on numerical values. Now, there are a lot of more subtle ways that we can think about numerical values in this, but these are variables that, the easy ones anyway, are the variables that naturally take on numerical values like age, height, income, value of a house, price of a stock. Qualitative variables, at least the ones that are easy to think of as qualitative, are ones that are categorical: person's gender, brand of product produced, yes, answers to yes or no questions, types of disease diagnoses. These are things that don't very easily naturally fall into numbered categories, although we very well can assign numbers to them. And we refer to those kinds of things as qualitative variables. And it matters a great deal whether or not the qualitative variables are the x variables, the independent variables, the predictors, or whether they're the y variables. If they're the y variables, then we use a different kind of problem-solving approach called classification. We think of problems that have y values that are qualitative as classification problems, and if they have naturally quantitative variables as the y values, we think of them naturally as regression problems. Quite different from the x values. If the x variables are quantitative or qualitative, it doesn't make too much of a difference. We can properly encode any kind of qualitative variable as if it were a quantitative variable for purposes of using it as an input to the machine. But much more of an issue when it's the output from the machine. So we have these two kinds of problems that we are thinking about. So this is yet another bifurcation that you have to think about when you're thinking about statistical learning problems. Is a particular problem a regression problem or a classification problem? And it depends entirely on the nature of the output, the nature of the y values. Okay, now let's talk a little bit about the homework. And I would like to, let's see, there are a couple of exercises that I'd like you to do. Exercise 2.4.1 and 2.4.2, and these are on page 52. And so what I'd like you to do now is pause the video or stop the video, whatever, and do these problems, review the text. You should spend some time. I mean, I've basically glossed over a lot of the text. I've tried to hit the high points, but the extent to which you need to study the details will vary from student to student, and the extent to which some of this is already sort of familiar to you will vary from student to student. So read the material over and write down your answers to these exercises, and then start the video again, and I will comment on the answers as I see them to these problems. By the way, you can always find the answers to all the problems in the entire book online, but my suggestion is that you not do that. If you're stuck, it's a good opportunity for learning. It's a good opportunity to write down what you think and try to make the most of what you think. Getting answers doesn't help much. If you just keep the video going and then listen to my answers and say, oh yeah, those make sense, that's what I would have come up with, that is not making you stronger. And the point of doing these exercises, like physical exercises, is to make you stronger. Okay, now take a long pause for you to stop the video. Okay, now, presumably a lot of time has passed and you've answered these questions. So now let me talk about my answers to these questions. So for exercise 1, we want to know whether or not we want a flexible or an inflexible method, whether we would expect a flexible method or an inflexible method to do better. And recall that we said that flexible methods are hard to interpret, and inflexible methods are very easy to interpret. So the sample size n is extremely large and the number of predictors p is small. This is the classic case for a regression problem. So I think that an inflexible method like regression is likely to work well in this kind of setting. This is exactly the setting for which regression is made. Then B, the number of predictors P is extremely large and the number of observations N is small. This is exactly the situation that commerce sites online find themselves in. They are able to gather a great deal of information about each customer, but they may actually not have that many actual paying customers, and they want to figure out how to run their e-commerce store. And this is exactly the kind of situation for which the very flexible and hard to interpret methods like support vector machines were invented. So that's what I expect to be the answer there. Third, the relationship between the predictors and response is highly nonlinear. Well, if the relationship between the predictors and the response, the true relationship is highly nonlinear, then we need a flexible method, because an inflexible method has only a very limited number of shapes that it can take on in expressing this relationship. So I would say in this case we would expect a flexible method to work better. And then finally D, and here's, I don't know the textbook answer, but I am going to guess that I will disagree with the textbook answer here. The variance of the error terms, sigma squared or var epsilon, is extremely high. What I believe the textbook is trying to lead you to think about here is the problem that was mentioned in the text, and I guess I didn't mention it in my recordings, of overfitting. And if you don't, so if the variance is high, you don't have a lot of information about what's going on. So there's a very, very good chance of overfitting. And so I think the textbook is trying to lead you to suggest here, if the chance of overfitting is high, you probably want an inflexible method. And I'm not sure that that's really the case. If the variance of the error terms is extremely high, the amount of variability that will be explained by your model is very low. It may or may not really be the case that an inflexible method works better, but I suspect that that's the sort of official answer, is that the problem that is being addressed here is the problem of overfitting. And that problem is much more salient in the case of flexible methods. And it's simply because of this tendency that they have to be able to take on a lot more shapes. Okay, now, so problem 2, explain whether each, and by the way, if you don't agree with my answers, that's fine. I just hope that you have paid attention to this part. Justify your answer. I hope that you have a good justification for your answer. That's quite important. The idea here is to get you thinking about these problems. Okay, now, is each of these problems a classification or a regression problem? And are we interested in inference or prediction? And what are N or P? So classification, as I just said, it means that the output variable is qualitative. Regression, the output variable is quantitative. Whether we're more interested in inference or prediction is whether we care about the machinery or we just care about the answer. And N is the number of observations and P is the number of X's. Okay, so here's A. We collect a set of data on the top, 500 firms. For each firm we record, okay, so already I can say that N is 500. So we have 500 rows, and we have several columns. We have, let's see, we record profit, number of employees, industry, and CEO salary. And we're interested in understanding which factors affect CEO salary. So P is going to be profit, number of employees, and industry. So those are the three inputs. So P is equal to 3. And then the output is going to be CEO salary. And let's see. And so we also want to know, are we interested in inference or prediction? Okay, so it says we're interested in understanding. So this is a key that we care about the machinery. We're interested in understanding the factors, which factors affect CEO salary. So this suggests that this is an inference problem rather than a prediction problem. We care about the what shape this function is going to take. And is it a classification or regression problem? So the CEO salary is naturally numerical, and so it is a regression problem. In fact, this is a typical kind of regression problem, and unfortunately, in real life, we find that CEO salary often has little to do with profit. CEO salary has been, at least in the United States, inflated grossly in the last few years, and it simply reflects the power structure in publicly held corporations. So this isn't going to turn out to be a very good model. This model isn't going to work. And I say that simply because I follow financial news a little bit, so I know that this problem exists, that number of employees in industry and profit are irrelevant. The power situation of the CEO in a publicly held company is what's relevant, and their salaries have inflated in the last, 25 years or something like that, have inflated vastly more than the salaries of their underlings. And the explanations for it are interesting. Okay, we are considering launching a new product and we wish to know whether it will be a success or a failure. So the outcome here, we already know just from this first sentence, from the outcome, we know that this is going to be a classification problem because success or failure is going to be a qualitative outcome. We collect data on 20 similar products, so that means that N is 20 that were previously launched. For each product, we have recorded 1, whether it was a success or a failure, price charged, marketing budget, competition price, and 10 other variables. So that's a total of, 14 variables? Oh, wait a minute. Now that's 14 including, so let's see, price, marketing budget. Okay, 13. So P is equal to 13. The 14th is whether it was a success or failure. The 14th is the outcome. So P equals 13 in this case. N equals 20. It's a classification problem. Are we interested in inference or prediction? For each product, we want to know whether it was a success, whether it will be a success or a failure. There's no indication here that we want to understand. I would guess that we just want to predict 20 similar products. I don't see any reason why we want to do inference here. It seems to me that we just want to predict success or failure. And in fact, given the small n and the large p, I'm going to guess that we're going to tend toward one of the more flexible models. Okay, we're interested in predicting the percent change in the US dollar in relation to weekly changes in world stock markets. So the output variable here is certainly going to be naturally numerical, so it's going to be a regression problem. Hence, we collect weekly data for all of 2012, so that would suggest that we've got N equals 52. For each week, we record the percent change in the dollar, so that's the outcome variable. The percent change in the US market, wait a second, percent change in the US dollar. Okay, so that's this is the output variable. So the inputs are change in the US market, change in the British market, change in the German market. So we have P equals 3. So those 3, this just does not make sense to me. The percent change in the dollar and percent change. Okay, so I'm a little puzzled by that. I think this is a little underformed, but in any event, P equals 3, N equals 52. We are predicting the change in relation I don't think that we want to understand what's going on here. I'm not sure I understand what's going on here. I would call this a prediction problem, and it's a regression problem. Okay, and so that's it for the problems that I've asked you to do. Now, there are all kinds of other interesting problems here that may be worth pursuing as well. I am concerned about the amount of time that we have, to discuss these things. So I'm going to be going on tomorrow to these two problems. And in general, the problems that I want you to turn in are going to be the applied problems rather than the conceptual problems. And they're fairly lengthy. These two, 2.4.8 and 2.4.9, are both quite lengthy problems, and they're going to involve using R, which is what we're going to be talking about a lot tomorrow. Well, we'll be talking about some other stuff too, but we will be. Oh no, I guess we won't. Tomorrow we'll just be talking about. Wait a second. So I've actually said I'm going to talk through this tomorrow before we do introduction to R. So I think there's a little bit of a mistake in the way that I'm pursuing this. Some of these things we can do without R, but some of them are going to require R. So I guess I'm going to have to give a little bit more on R tomorrow than I was planning to. But basically, I'm interested in pages 29 through 42 for tomorrow. So I hope you have a good time studying pages 15 to 28 today, and I look forward to talking to you tomorrow.